Hello, my name is Hitesh, and today I will be presenting my solution for round one coding task. So, my project is titled SAM to Refine Adaptive Memory Aware Video Segmentation. So, the core task was to select a recent paper in ML and propose a unique solution. I choose to focus on challenge of long-term object tracking in videos, especially how to make state-of-the-art models like Segment Anything Model 2 or SAM2. Uh, so, what is core problem? In application like autonomous driving perception system need to track objects like pedestrians or other vehicle frame by frame continuously. However, these objects are frequently occulted. They might go behind a pillar or tree or another car. While powerful model like SAM2 are excellent at segmenting what they can see, but they lack intrinsic long-term memory. What an object disappear and reappear, the system can lose track and take too long to reacquire it. So my work builds upon a paper by Yin and colleagues, which propose combining SAM2 with Kalman filter for motion prediction. This is solid baseline, but it has limitations. It believes on a fixed confidence threshold and doesn't have a mechanical mechanism to preserve object shape during occlusion. So this led to three core research questions. How can we use the history of tracking quality to create adaptive gate, making the system more flexible than fixed threshold? Can we build a lightweight memory system to store and recall high quality mask, helping the tracker recover an object shape, not just its position after an collision? And third question that comes to mind, what kind of automated tooling can we build to make these experiments reproducible and result easy for stakeholders to analyze? So to answer these questions, I conducted a literature survey focusing on three key areas: prompt segmentation models. So, the original SAM paper by Kirillov and its successors like SAM2 are revolutionary. They can segment almost anything given a prompt. However, they operate on short term frame by frame basis and lack temporal context needed for robust video tracking. And second was motion edit tracking. This is classical field with foundational algorithm like short and deep short that use Kalman filters to predict object detection. These are efficient but typically operate on simple bounding boxes. Third is memory network for video segmentation. Advanced model like XMEM and STM use sophisticated deep learning techniques to build memory of object. So while powerful, they are computationally heavy and often act like a black box, making it hard to extract the quality metrics. So this review revealed a clear research gap. There is a need for a lightweight, analytical friendly system that enhances SAM2 with both adaptive logic and memory without overhead of full-blown memory network. So my project SAM2 Refine is defined to fill this exact gap. So what is SAM2 Refine? It is end-to-end pipeline that enhance a standard SAM2 plus Kalman filter tracker with two novel components. So as from this architecture diagram, we can see instead of using uh, fixed confidence score like zero point 0.5, this module maintains a rolling window of recent prediction scores and mask size. It calculates a dynamic adaptive threshold. If system has been tracking confidently, the threshold remains high. If quality dips, the threshold lowers slightly, allowing the system to reacquire the object more easily without becoming unstable. This is implemented in this file quality controller.py file. So the second innovation is memory manager. The quality when the quality controller confirms a high quality mask, it is stored in short-term buffer. If the tracker loses the object, it enters an occulted state. Instead of just guessing the location, it queries the memory manager. The manager retrieves best recent mask and uses an affine transformation to wrap it to Kalman filter. And this is implemented in memory manager.py file. And So let's now quickly walk through the life cycle of single frame. First, we get a new frame from video, SAM to predictor generate a mask and confidence store. This pair sent to quality controller, which calculates the adaptive threshold and determines if prediction is reliable. If it's reliable, mask is used to update the Kalman filter. Mask is stored in memory manager. The frame is marked as tracking. If it is not reliable, the system declare an collision. Then it queries memory manager for best historical mask to fill in the gap. Finally, the system logs all relevant matrices like IOU, centroid error, visualizes the output. So the entire logic of this system is basically orchestrated by this pipeline.py file. So and the core fusion happens in this occlusion handler py file. Now I would like to explain about the experiments, the two experiments that I run. The first tag propose runs my full SAM to refine solution. The second tag baseline KF disables the adaptive quality and memory feature to simulate the original paper approach. So the pipeline automatically generates output video matrices, diagnostic plots for each run. So, for example, like we have this output video dot, this proposed one. So in the beginning, you can see the object is being tracked with high confidence. And the overlay is green, and the status is tracking the quality score shown at top left is well adaptive threshold. Now at frame 41, object disappear, simulating a collision. The system immediately detects low quality score, and the status change to occulted KF prediction. And the overlay turns red critically because of the memory manager. We are not just showing a dot, we are showing plausible mask that has been carried over the memory, preserving the object shape. At around frame 60, the object reappears. The adaptive quality controller have lowered the threshold slightly during the occlusion, allowing for swift reacquisition. The system immediately returns to tracking state, and green overlay successfully uh, tracked an occlusion event. So this basically demonstrates the robustness that my proposed module add to the baseline system. So we also have metrics reports. So these are the metrics reports uh, of different systems. And for the metrics like intersection or union and tracking ratio, both perform identically on this simple synthetic data set. This is a good sign. It means my improvement didn't compromise baseline performance. But the key insight is the mean threshold column. The baseline uses a fixed threshold of zero point 0.5. My proposed solution, however, operated at an average threshold of 0.43. The 13% reduction demonstrate efficiency of adaptive system. It can maintain the same tracking accuracy while being less rigid its requirements, which is crucial for handling noisy real world video where perfect scores are rare. So I also documented it in case study and research report.md files. I have also added 25 DI backed references in the research report. And the case study basically explains which frames this work in business context for autonomous perception pipeline, outlining objective and recommendation. Furthermore, as required, I developed a publication strategy. My reports research identify five target journals, including sensors and IEEE access, which are reputable, cost-effective Q2 journals well suited for this type of application-focused research. Several of my did references come from both targeted journals aligning with my work scope. So, in conclusion, SAM2 redefines successfully extends a baseline occlusion. Extends a baseline SAM2 tracker with unique solution to handle occlusions. Its two key contribution: adaptive quality gating and memory aware recovery, create a more resilient, efficient, and practical system for real world value segmentation. The entire project is delivered as reproducible and document and properly documented. And this concludes my presentation. Thank you for your time and attention.